All right, let's go ahead and get started. I want to welcome you back to Unit 15. This is acid-base equilibrium and buffers. And we were talking last time about a problem that involved something called the 5% rule. And I want to get back to that and understand what we mean by the 5% rule and when we apply it. So in this problem, and I'll read the problem again, it says calculate the pH of a solution which is 0.712 molar methylamine or CH3NH2 with a Kb of 4.4 times 10 to the minus 4. And you recall from last time that we did the Rice table, we set up the reactants and the products. This is a hydrolysis reaction. And at the end, on the equilibrium line, we got an X for the ion, the CH3NH3 plus, and the OH minus, also X. But for the methylamine, the equilibrium concentration was 0.712 minus X. But in the calculation, we ignored that minus X part. See, we said 4.4 times 10 to the minus 4, which was the Kb, is equal to X squared, X times X, over 0.712. But where's the minus X? It's not there. So here's that minus X in the equilibrium line. But we chose to ignore it. Why did we do that? First of all, let's answer the question of why we did that. Why did we ignore that minus X? Well, we did it because, and by the way, this may sound totally foreign. You know, in math, certainly you can't just say, well, I'm just going to ignore it because it just makes my life easier. There's a reason why, but let's talk about why we did it. The reason we did it was because if we had placed a minus X right there, 0.712 minus X times 4.4 times 10 to the minus 4 equal X squared would have set up a quadratic equation, right? And not that quadratic equations are terrible. In fact, in my classroom at Clark High School, if you were one of my students, you are going to be required to do that type of quadratic equation. Now, if you're from a different high school, or maybe you're in California or in Washington, your teacher may not require that. But here at Clark High School, I'm going to require that you, so bear in mind, my students, you are going to have to do that quadratic maneuver. But on the AP exam, you can ignore this X, okay? You can simply pretend like it's not there, that X right there. And you're going to have to justify it, but you can do that to make your life a little bit easier. And it's because of something called the 5% rule, okay? So let's talk about the 5% rule and how we use the 5% rule to justify our ignoring that X. So what the 5% rule says is this, is that if the amount dissociated is less than 5% of the original concentration, then you are allowed to neglect that X. Okay, let me say that again. If the original, or excuse me, I should say, if the dissociated amount, in this case that would be, say, this right here, is less than 5% of the original amount, that's this right here, if the dissociated amount is 5% or less of the original amount, then you're allowed to neglect that X because the X was not big enough to really make any difference, right? So let's check. Well, what was that X? Well, we determined in the problem that that X was this number, 0.018. So that was the dissociated amount, 0.018 divided by the total amount, or the initial concentration, which is again 0.712 times 100. Well, that's only 2.5%. That's less than 5%, isn't it? That means that what we can do is we can say that this amount, I'm going to make it kind of a long arrow this way. We're going to say that this amount, that X right there, is negligible. Okay? Negligible. That means there's not enough to make any difference. But I still have to justify it using the 5% rule. I have to actually show my math to show on the AP exam that it is negligible, right? Using the 5% rule. Again, Clark High School students, I want to make it clear to you. If you are in my class at Clark High School, San Antonio, Texas, then you are not allowed to, if it's if it's a quadratic that is required, then you're required to show me that work, okay? All right? And certainly you would have to do that in college. So that's why I'm requiring it here in my classroom, okay? So I just wanted to make sure that everybody was clear on that, okay? On why I apply, how I applied, and why I applied the 5% rule. Okay, folks, I've got a couple of slides here. I'll let you go over them. Hydrolysis of salts, and there's a few here that I'll let you do on your own, okay? And I want to move on to, there's another one here, and so I want to talk about basic, acidic, and neutral salts in those slides, but I'd rather just use this time to solve a problem or two, and so I'll let you read those on your own, okay? You have access to those notes. All right, I just want to go over this slide, just take a few notes here. Hydrolysis of salts. It says salts are ionic compounds which are formed in a neutralization reaction between an acid and a base, right? So we talked about salts and how they are formed from an acid and a base. When you put an acid and a base together, you get a salt and water. So I want to talk about those salts now and how we can determine their pH, or at least estimate their pHs when they undergo something called hydrolysis. It says salts can be characterized from the type of acid or bases which combine in the neutralization reaction. So salts can be formed from the reaction of a strong acid and a strong acid and a weak acid and a weak base, or a weak acid and a weak base. So I want to write here, or I have written, 3 different salts, okay? So I have NaC2H3O2, right? I have NH4Cl, and I have NaCl. These are 3 salts. And I want to try to determine what's going to happen when I place these salts into water. Is it going to form an acidic solution, a basic solution, or a neutral solution? So let's take a look at the sodium acetate first, right? So if I put sodium acetate into water, I want to think about, first of all, what the parents were that the sodium acetate came from, right? What did it come from? Well, the sodium came from sodium hydroxide, right? That's the base. And the acetate ion came from acetic acid, right? It's HC2H3O2. So we're going to ask the question, first of all, is this a strong acid or a strong base or a weak base? And is this a strong acid or a weak acid? Well, as it turns out, NaOH is a strong base and HC2H3O2 is a weak acid. Acetic acid is a weak acid. So that means that this one is the stronger of the two. It's a strong base as compared to the weak acid parent. So that means that my prediction is going to be that when I put the sodium acetate in the water, it's going to form a basic solution, just like that. Okay? It's going to form a basic solution. Now, let's go to NH4Cl, ammonium chloride. What were the parents that the ammonium chloride came from? What were the acid and the base? Well, what did the ammonium come from? Well, it came from ammonia, right? It came from ammonia. And the Cl minus came from hydrochloric acid. Ammonia is a weak base, but hydrochloric acid is a strong acid. So strong acid beats weak base. This one is going to be acidic, right? So if I dissolve NH4Cl in water, I'm going to get an acidic solution. The last one is NaCl. Where did it come from? Well, the sodium came from a parent of NaOH. That's the base. The chlorine came from HCl. That's an acid. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. So they simply cancel each other out. Strong acid with strong base, I'm going to get a neutral solution, okay? When you have 2 parents that were strong, one strong acid and one strong base, you're going to get a situation in which you have a neutral solution, neither acidic nor base. Now, let's talk about the hydrolysis way of determining what we've already determined, whether these were acids or bases or neutral. All right. I want you to go back to the parents, right? The parents of that created these salts. Let me scroll up just a little bit, okay? And my question is, what is the ion that was produced by the sodium hydroxide? Well, it was Na+. Well, what was the ion that was produced by the acetic acid? Acetate ion, C2H3O-, right? Combine them and you get NaC2H3O2, right? Now, here's the rule. Listen very carefully. The ion from the weaker parent undergoes hydrolysis. The ion from the weaker parent undergoes hydrolysis. Sodium hydroxide was not weak. It was strong, right? It was strong. But acetic acid is weak. That makes the acetate ion the weaker of the two ions, right? Or excuse me, I should say it is the ion that comes from the weak parent, right? That's the one that's going to undergo hydrolysis. So let me write the hydrolysis equation. C2H3O2-, that's the ion in question, that's the ion from the weaker parent, plus H2O in equilibrium with, well, what, you have to have a transfer of a proton here. That's what a Bronsted-Lowry reaction does. You have to have a transfer of proton. Well, the proton is going to go from the water to the acetate ion to form acetic acid and OH-. So we have HC2H3O2. So what did you produce? You produced hydroxide, right? Well, Bronsted-Lowry bases produce hydroxide. So that's the real reason that we classify this salt, the NaC2H3O2, as a basic salt, okay? A basic salt. Let's do the same thing with the NH4Cl. Now, we've said that the NH4Cl salt was acidic. We said that because of the fact that HCl was stronger, was a strong acid, and H3 was only a weak base. So let's take the ion from the weak base. Remember, it comes from the weak parent. So what was the ion from the NH3? What did we get from the NH3? We got NH4+, right? We also got Cl- from the HCl, but we don't care about that. We only care about the weak parent. So we're going to say NH4+ plus H2O is going to be, that's the hydrolysis equation, in equilibrium with transfer of proton. NH4+ is going to lose a proton to the H2O, yielding NH3 and H3O+. What did you get this time? You got H3O+. So that's the real reason that NH4Cl is an acidic salt, right? All right, getting the hang of this? All right, let's go to NaCl. Now, we said that NaCl is neutral. Why? Well, neither one of these is weak. So that means we're not going to have a hydrolysis. All we've got is the pH of water, and the pH of water is 7, right? All right, so now I've given you two ways of determining the acidity or basicity of salts, right? We can just look at the parents and see which was weak and which was strong, but I also want you to be able to write a hydrolysis equation. So this right here, let me put in a different color so you can see clearly what I'm looking for. Let's do it in green. No, that's already green. Let's do it in this color right here. This right here is a hydrolysis equation, and that's what I expect you to be able to do. This is a hydrolysis equation. I expect you to be able to do a hydrolysis equation for a salt, whether it's a basic salt or an acidic salt, okay? Of course, again, if it's a neutral salt, there is no hydrolysis and we don't worry about it. All right, folks, I think that's going to be it for this one. I'll see you in the next one. Thanks. Bye-bye.